Let's take a look at finding the area enclosed by a curve, and typically the x and y axis, or maybe it's enclosed by an axis and two different curves, or maybe it's just enclosed by three different curves. But this particular video we'll call part one, and all of these are going to be in terms of x. Meaning when we look at an area, how are we doing this based on calculus? Well, let's assume that you've already discussed LRAM and RRAM and that you understand the principle behind that we're going to find the area enclosed. So let's take this first one. This is just a nice easy line, y equals 6 minus 2x, which is graphed in red here. And we're going to find the area enclosed in the first quadrant, meaning bounded by the y-axis, x-axis, and our curve. Okay, and what we're going to do is that we know really what we're doing is we're going to divide this into an infinite number of rectangles, sum up all these rectangles, and then get the area. Okay, so when it comes down to it, we need to get a graph, we need to find intersection points, and then we just need to integrate, right? The only calculus part is right here. And I would say, honestly, that's the easiest part. Most of the time, students struggle with graphing and then finding the intersection point. We still don't have a real good grasp of how to grasp these things by hand without a calculator and or finding intersection points. That's honestly the harder part for people, or figuring out what the area they actually want you to integrate. The integral is not usually very hard and can be easily checked with a calculator. So let's find this first area. And so let's get some points here. The x-intercept corresponds to a y value of 0, y equals 0 when x equals 3. So that's the point 3 comma 0. Not that it really matters in this case, but that is 0 comma 6. And we're going to sum up all these rectangles. So we're going to sum up all the rectangles from 0 to 3. Each rectangle has a height of 6 minus 2x and then a width of dx. Again, that's the theory behind it, right? Each one of these rectangles has that height, width of dx, sum up all of these individual area of rectangles from 0 to 3, and that gives you then the total area, okay? So when we do the integral of 6 is 6x, the integral of negative 2x is negative x squared, and then we evaluate it from 0 to 3, meaning we plug in 3 and get 18 minus 9, which is 9, and then we plug in 0, and of course we get 0, and so we claim then the area is 9. We can check this with geometry. Using geometry, we know that this is 3, and this is 6, and the area of any right triangle, or any triangle that is 1/2 base times height, which also then produces 9. Again, we've checked our calculus with what we know our geometry. Now, geometry probably only works in this example because this is a triangle, and none of these other shapes are typical geometric shapes. They're not triangles or trapezoids or rectangles or circles or stuff. Okay? But the theory is we're going to turn all these into LRAMs and RRAMs, and there's an infinite number of them. Okay, let's do this next one. So we're going to take all these rectangles and we're going to add them up. This intersection, of course, is the origin. Sine of 0 is 0. And then sine of pi is also 0. Think of your unit circle. So we need to integrate then from 0 to pi of sine x dx. Again, sine x represents the height of each one of these rectangles, dx represents the thickness, and we're going to sum all of these things up. The integral of sine is negative cosine x. Evaluate from 0 to pi. When you plug in pi, you're going to get negative cosine of pi. Negative cosine of pi is negative of negative 1, so that's 1. Minus plugging in 0. Plugging in 0 is negative cosine of 0, negative 1. And you get 1 minus a negative 1, and you get 2. So we've just decided that any arch here of any hoop of sine, or in fact cosine, ends up being 2. It's exactly 2. It's kind of interesting that we evolve a trig function and we integrate from 0 to pi and then we get exactly just 2. But that's what it is. So we know that area. Okay, come down here, same thing. We're going to take rectangles and we're going to sum them up. And in this particular case, the rectangles don't go all the way down to an axis. But that's okay. We still just need to find an equation that gives us this length. But that's easy. That's just the top curve minus this bottom curve. And I've graphed it for you. And again, I would argue that graphing and finding these intersection points are probably the hardest thing to do. But this is e to the x. E to the 0 is 1. and then it zooms off like an exponential. I'm bounding it by y equals to 1, and then x value, natural log of 5. Okay? And the nice part about the natural log of 5 is that we know that this point then, e to the natural log of 5 is just 5. So we know these points. Now, again, this y value is not going to really matter in this particular case, because what are we going to do? We're going to sum up all those rectangles from 0 to the natural log of 5. What are the heights of our rectangles? Well, it's just top curve minus bottom curve. This length, which is this y value, minus these y values. So it's just e to the x minus 1, right? This is just y equals to 1 dx. Okay? The integral of e to the x is e to the x. The integral of 1 is just x. Evaluate from 0 to the natural log of 5. When you plug this in, you're going to get the natural log of 5. Oops, excuse me, you're just going to get 5. Well, I'll write that better. E to the natural log of 5 is 5, minus the natural log of 5. That's what you get when you plug in 5, minus what you get when you plug in 0. When you plug in 0, e to the 0 is 1, minus 0 then is just this. And so the whole answer then is just 4 minus the natural log of 5. Okay, so that is the exact answer. Again, this area just ends up being some irrational number. Now, let's be clear, okay? All of these, and again, I started out slow, and then I'm going to do 3 harder ones. So these are kind of the easy ones. Every single one of these things, as long as we're looking at x, the area is just the integral of the top curve minus the bottom curve dx. Every single one. Top curve minus bottom curve. Top curve minus bottom curve. Now the bottom curve was just y equals to 0. So you don't see it in these problems, but it's there. We always want this height. Well, this height is always this curve minus this curve. It doesn't matter that you're in the first quadrant, third quadrant, fourth quadrant. It doesn't matter where you're located at. If you take top minus bottom, you're always going to get this distance. Okay, let's come down here and I'm going to come up with some new example. Okay, so again, if you had some curve that looked like this is some quadratic down here. And then let's say you had some line that went like this. Okay, and let's say you wanted this. Isn't it still just top minus bottom? Think about it. The red here is like -2, and this is like -4. So if you take the top curve, -2, minus a -4, you're still going to get a +2. If you want this distance, it doesn't matter what quadrant you're in. If you take the top and subtract the bottom, you will get this length, and it will always be a positive, assuming you do top minus bottom. Again, top is always has the higher y value. Subtracting a lower y value will always net you this distance. And again, all of these examples would probably be in the first quadrant, but it doesn't matter what quadrant you're in. If you wanted to find this area, you would integrate this quadratic minus this line from 0 to whatever this intersection point was. Again, this is key. Always going to be true, no matter what. As long as you're in dx, it's always top minus bottom. And again, if you're thinking forward, if we wanted to go the other direction, it's going to be right minus left in dy, but that'll be the next video. But in this one, we're just sticking with x. So let's do this next one. We have some quadratic, and we have some line, and we want this area kind of bounded in this first quadrant. So again, we're going to fill this with rectangles, and we're going to add up all the areas of the rectangles. I went ahead and plotted this intersection, 3, 6. Again, when x equals 3, y equals 6, 2 times 3 is 6. 15 minus 3 squared is 6. So the intersection of this quadratic and this line is this. And again, you have to graph this. You have to graph this. Boom. You have to find the intersection point. Because if you don't know the intersection point, how do you know how far to integrate? And so those are necessary things that you have to do at the beginning that I kind of just did for you in this video. So let's integrate from 0 to 3, right? We're stacking these rectangles from 0 to 3. And the rectangle's heights are what? What's this distance? Well, it's just this curve, this y value, minus these y values. So take 15 minus x squared, and then minus 2x dx. We do this integral, 15x minus x cubed over 3 minus x squared, and evaluate from 0 to 3. Okay, when you plug in here, you're going to get 45 minus, 27 over 3 is 9 minus a 9. Okay, so what is that? 45 minus 9 minus 9. I guess that's just 27. Yeah, that's no big deal. And then when you plug in 0, you get 0, so great, you don't even have to subtract. So we know that area is exactly 27. Well, that's kind of nice. Might turn out to be a nice, easy number. Okay, all right, let's do this next one. Oh, wait a second here. This one's a little different. Let's see why. So we're going to stack, 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 stack. Oh, what happened? Well, we have to change because we have a whole different curve that dictates the height of these things. So this is an example where the top and or the bottom changes. In this case, it's the top curve changes. So if you're integrating and somehow the top changes or the bottom changes, well, you're going to have to split up the integral and do two separate integrals. This total area, hopefully you can see, it's just the area of the red plus the blue. Okay, so let's do the red. What's the red? Integrating the red, we'd go from 0 to 4. And again, I found this intersection value for you. Square root of 4 is 2. Boom. 6 minus 4 is 2. Okay, this intersection point is 4 comma 2. Again, you had to find that. You have to find that this intersects at 6 comma 0, which is pretty easy in this case. So if we want to find the red, accumulate from 0 to 4 of this curve, and then add it to the accumulation from 4 to 6 of this curve. Okay, so I have to break it up into two separate parts. Okay, the integral of half of x, just remember the square root of x is x to the half, so we're going to increase the power by 1 and then divide by the new power. Dividing by 3/2 is multiplying by 2/3. We're going to go from 0 to 4 on that one, okay, plus 6x minus x squared over 2, evaluate from 4 to 6. Okay, so let's do this one. Plug in 4 here. 4, square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16, 16/3. And then subtract plugging in 0, but that's just 0, so we got this. Okay, so this red is 16/3. Plus, plug in 6. 6 times 6 is 36, 36 minus 36 over 2, 36 minus half of 36 is 18. Minus plugging in 4. Plugging in 4 is 24 minus 8. 24 minus 8 is 16. So this whole thing is just 2. So 16/3 plus 2 is 22/3. And again, you can check the blue real easy because it's just a triangle. Remember, the blue is just that. It looks like it's too high. And from 4 to 6, well, it's only 2. So that's a terrible picture, but a 2 by 2 triangle is just an area of 2. Add that to the area of the red, and boom, we have this area. Again, you have to do two separate integrals if the top would change or the bottom would change over the integration. Okay? All right, let's do two other ones, and then we'll be done. Okay? So this one is probably the hardest to graph. And again, I did graph it for you, but you have to be able to do this on your own. So I looked at a quadratic, y equals x squared minus 2, and the line 2x plus 1. You have to forgive me for the fact that this is really 1 comma 1. I know it should probably be right there, but it's close enough to be realistic. So you have to find these intersection points. And again, you can just graph both of these on your calculator, but you should also be able to do these by hand. This is a line, and this is a nice symmetrical quadratic. 3 comma 7, so 9 minus 2 is 7, sweet. 2 times 3 plus 1 is 7, great, and they hit here. And over here, negative 1 times 2 plus 1 is negative 1, and then negative 1 squared minus 2 is also negative 1. Okay, so we've kind of just checked to make sure that I did that right. So what do we want to do? Well, we want to add all these up. And again, this is a great example where some of the areas in the third quadrant, second quadrant, first quadrant, fourth quadrant, but it doesn't matter. The red curve is always on top, and the blue curve is always on bottom. And so if you accumulate from negative 1 to 3, again, accumulate to the x values, and you take the red, which is 2x plus 1, and you subtract the blue, x squared minus 2, this function, red, minus this function, blue, will always give you this length, no matter what quadrant you're in. That length is the length of your rectangles. Dx is the width of all the rectangles, and then sum them all up. Okay? Now, this integral maybe is a little messier than you're used to, but it'll work out. And when you do this particular one, do I have even the notes for this one? Oh yeah, it's not too bad. It ends up just being 32 thirds. So we can do this integral. We can simplify right away if we wanted to, but we don't have to. See how this is a minus x squared and this is a minus minus 2. So I'll go ahead and rewrite it. Why not? Okay, so this is just 2x. This is a minus x squared. And this is a 1 minus a negative 2. So that's just a plus 3. Okay, now let's do the integral. The integral of 2x is x squared. X cubed over 3 plus 3x. Evaluate from negative 1 to 3. Okay, so let's plug this in. 9 minus 27 over 3. So that's 9 minus 9 plus 9. So that plugging in 3 gives us 9. Okay, plugging in negative 1 is going to give us 1 minus negative 1 cubed. Well, that's just a minus and a minus. So that's 1 plus 1/3. Better write this one down. 1 plus 1/3 and then minus 3. So that's 9 minus, and that's going to be 4/3 minus 9/3. It's going to be negative 5/3, but then you're going to add it, so it's plus 5/3, right? Minus a negative 5/3 is plus 5/3. So this is 27/3. So this is then 32/3, which is the same thing as 10.6 repeating. Okay, awesome. Again, I'm going to stand by my argument that the hardest thing is to actually graph the functions correctly, find the intersection points. I really just don't think this integral step is really that hard. These integrals are pretty easy, and you just got to be careful kind of plugging in. Most people struggle with the graph. All right, we'll do this last one. So let's say I give you this circle, and I have no idea why I wrote it y squared plus x squared. I know it's usually written x squared plus y squared, but I didn't feel like erasing it. So this is a circle with radius 4. So again, you have to know a little bit about algebra to know that this is a circle, and it does have a radius of 4, which means you know this point here is 4, 0, and this point is 0, 4. And all I'm told is I have this line segment that goes from here to here, and what I want is this area. Well, the first thing you want to need to do is figure out what this curve is. Well, it turns out that the red curve, if it has a y-intercept of 4 and it has a slope of negative 1, well, that's actually pretty easy. That's just negative x plus 4. Okay, that's not too bad. You cool with that? And again, you can write it any way you want, 4 minus x. And then this circle, well, we really want this blue curve, so that tells us that y is going to be the square root of 16 minus x squared. And again, we want the positive version because we want this up top. Okay, so what are we going to do? We're going to sum up all these rectangles. These rectangles, we're going to sum them up from 0 to 4 of the top curve, 16 minus x squared, minus the bottom curve. Make sure you use parentheses, negative x plus 4. And it's going to turn out you're lucky on this one. You can't do this integral yet. If you get to BC, you can probably do this integral, but it's going to take you some time. It's not going to be worth it. You're okay. You're just going to use your calculator. I'm just going to remind you, go ahead and hit Math 9 and tell the calculator to do this for you. And when you tell the calculator to do this for you, it's going to give you an answer. The best part of this one is you can check it. Okay? You can check it because this one, you can do geometry. That's why I like this one, because it reinforces the fact that geometry will actually give you an exact answer. This is just going to give you some random decimal. So let's check it out. What does the geometry say? Well, I can do a quarter of a circle. So a quarter of pi r squared. That would get me like this whole thing. All of that. I only want that. But I could take the quarter circle and I could subtract that triangle. Well, that triangle is easy. Subtract 1/2 base times height. So I get 1/4 pi of 16 minus half base times height, minus 8. Okay, so it turns out that this is exactly 4 pi minus 8, which you can confirm will give you the exact same random decimal that you got up there. Okay, so this is finding the area between curves. I tried to do a bunch of popular curves. I gave you an example where it was really easy. It was just take the integral of the function, find some intersection points. I gave you an example where there was a bottom curve, where there was space there, and so the height of the rectangle was top minus bottom. I gave an example here where the top curve actually changed what it was, and so you have to break it up into two separate integrals. This one's probably the most AP-like in terms of you actually had to find some of these harder intersection points, and it was in all four quadrants, which I think was interesting. But again, you're still just stacking rectangles. The length of the rectangles is just going to be the top curve minus the bottom curve, and you go from there. This one was kind of cool because I didn't really even tell you that function, and you could check it with geometry, which I also thought was interesting, that the geometry was the more sophisticated way because it actually gave you an exact answer. Okay?